when we look in the stars, we're looking at the light of the stars. When we look at galaxies, we look at the light of the stars. Uh, we always look at the light of the stars. All the objects in space, uh, they're all really far away. We've had a spacecraft that have been to the moon and brought back samples. We've had unmanned missions to a couple of nearby asteroids. One of them brought back samples. We've had missions that have been to comets. We've had missions that landed on Mercury and Venus and Mars. We've had spacecraft that flew past some of the other planets. But most of the time, even when you get a spacecraft to a planet, you're in orbit around it. You're not studying it or passing by it. You're not actually studying it the way you would biology or chemistry or something else in the laboratory. In biology, you want to see how a frog works. You slice it open and look what's inside. In chemistry, we can pour chemicals together and see what they do. For astronomy, we're stuck with just looking at it. So that means that we need to understand how light works, the physics of light, in order to understand the things we're looking at. How does light work? That tells us what we're looking at. So that's our next set of topics here, is how does light work? Isaac Newton experimented with light, and as Newton was looking at light, he put white light through a prism, and he saw that the different colors of light kind of break out into a rainbow. And he realized it was always the same. The least bent was always red, and the most bent was always a violet color. And so he realized he always get the same range of colors. And he actually, referred to them as red, orange, yellow, green, blue, indigo, and violet. For me personally, indigo and violet look pretty similar to me. They both look kind of purple. Okay, so I think of it as red, orange, yellow, green, blue, purple. But it's not really purple. Really, technically, violet and purple look alike, but they're different. But he used 7 because he thought 7 was a complete number. And he was into numerology and so forth, and 7 was significant to him, and so he picked 7 colors to represent these primary colors. And so it was always red was the least bent going through the prism, violet was the most bent going through the prism, green was in the middle. This was the order of the colors. For students, it's been very useful because you can imagine this is like a guy's name, Roy G. Biv, and you can remember the color. Then he got to thinking, well, what about those colors? I look at colors, like green, and there's like all these different shades of green. And so, if you were to take the green light or one of these other colors of light and run it through another prism, would it break out into little subcolors? And what he discovered was, no, it didn't. That if you had, in this diagram here, yellow light going through another prism, rather than breaking out into lots of different kinds of yellow, it took this yellow light that was bent by a certain amount in the first prism, and it bends it by the same amount here. So each of these colors is really a pure color right there. And so so that means if you were to take all these different colors and put them back together, you'd get white light. Now, I wish we were in class, because this is actually a chapter that I really enjoy teaching about, because I wheel a big cart full of demos into the classroom and we demonstrate all this. So I have these projectors. I have that projects a red spot onto the screen in the front of the room, and one puts kind of a yellow-green spot in the middle of the room, and one that kind of puts a bluish purple spot in the middle of the room, and each color is pretty much distinct, but when I put them all together, it's white light. And so it proves that, in fact, that the white light is really made up of all these different colors. Okay. Well, next question, how fast does light travel? Galileo Galilei, he's famous for pointing a telescope at the sky and realizing, oh, cool, there's cool stuff up there, and a variety of other things. But One of the things he did was he also worked with light, did some physics here trying to study how light worked. And the way he did this was he would stand on a hill somewhere, and here he is standing on a hill, and he has a lantern and a little shade on it. And he has a friend standing on another hill with a lantern and a shade. And so what Galileo did was he would uncover his lantern, and the light would travel over to the other person who would see it, uncover his lantern, the light would travel back, and in the meantime Galileo is taking his pulse to figure out how many heartbeats it takes for light to go from one hill to the other and back. And what he discovered was it was essentially instantaneous. He realized it was so fast that was less than a heartbeat, so he had his friend stand further away and kept getting the same result. Basically, the light traveled back and forth faster than his friend's reaction time. And so Galileo concluded that light must travel instantaneously. Now, that's a wrong conclusion, but it certainly was traveling much more quickly than he was able to measure. The first real measure of the speed of light was a fellow named Ole Reaumur. And Reaumur was looking at the moon's Jupiter. Now, remember, navigation is related to where you are. I mean, in other words, what you see in the sky depends on where you are on Earth. So navigation is very closely tied to astronomy. And in fact, many of the early observatories were funded for the purpose of navigation, providing tables and charts for people that were studying, the mariners that were out at sea, and able to needed to be able to measure where they were. Now, one of the things you needed was an accurate way of telling time. And on a ship, that was very difficult to do because the most accurate clock they had in those days was a pendulum clock. And a pendulum clock would get off if the ship was rocking. And so what Reaumur realized was that for a clock, you could use the moon to Jupiter, because Jupiter's moons go around Jupiter in a very regular pattern. So you see a moon going into the shadow behind Jupiter, and you know exactly how long it takes to go into the shadow again. And so you can calculate way into the future when this is going to occur. And so that way you'd have these tables of these events, and someone like Magellan sailing around the world would stop at an island, set up a telescope, and in order to figure out his longitude, he wouldn't have to know what time it was exactly. And so he would look at Jupiter and see exactly when this moon was passing the shadow, and he knew what time that's supposed to happen on a particular day, and so he knew what time it was. And at least he knew what time it was in England. He'd find out what time it is where he's at, and the difference in time would be related to the difference in longitude. And that worked fine with one small problem. When Jupiter and Earth were very far away from each other, the moons looked like they were moving into the shadow late. Well, why? Well, because light had to travel a farther distance. So when it's up close, it takes a certain amount of time, but if it has to go farther, then it took longer, and so you saw it happen later. And so Reaumur was able to realize that it takes light about 8 minutes to go 1 AU. So that means we see the sun 8 minutes ago. When we look at the sun, we're seeing light that left the sun 8 minutes ago. And likewise, you would see the Jupiter's moons doing their things a few minutes late because the light had to travel a little bit farther to go across the solar system. And so this was the very first measure of the speed of light, 8 minutes per AU. So once they were able to figure out how big an AU was, then they had a measure of the speed of light. Speed of light is about 300,000 kilometers per second. That's 186,000 miles every second. That's the speed of light. In the calculator, the easy way of writing it would be 3 times 10 to the 8th meters per second. So this is the speed of light.